Hello, and welcome to the Cozy Curiosity channel. Tonight, we're going to look up at the night sky together and explore 100 fascinating facts about stars. Those ancient points of light that have guided travelers, inspired poets, and held the secrets of the universe for billions of years. From the smallest red dwarfs barely glowing in the cosmic darkness to massive supergiants that dwarf our own sun, stars are the universe's storytellers, carrying tales of creation, transformation, and the endless cycles of birth and death. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. So settle in, let your breathing slow, and allow your mind to drift among the stars as we uncover their beautiful mysteries. Whether you're here to learn, relax, or simply let sleep wash over you, these gentle facts will guide you through the night. Let's begin. Stars are giant balls of hydrogen undergoing nuclear fusion in their cores. When you look up at a star twinkling in the night sky, you're witnessing something extraordinary. A massive sphere of mostly hydrogen gas, so hot and dense at its center that atoms are literally fusing together. Deep in a star's core, temperatures reach millions of degrees, creating pressure so intense that hydrogen nuclei overcome their natural repulsion and crash together, forming helium and releasing enormous amounts of energy in the process. This nuclear fusion is what makes stars shine, generating the light and heat that travel across vast distances to reach our eyes. Without this cosmic furnace, stars would simply be cold, dark spheres drifting through space. The energy produced in a star's core takes thousands of years to work its way outward through the dense layers before finally escaping as the starlight we see, meaning the photons reaching your eyes tonight began their journey long before you were born. The Sun is actually a very average, medium-sized star. Our Sun feels enormously important to us, and for good reason. It sustains all life on Earth. But in the grand cosmic scale, it's remarkably ordinary. Classified as a yellow dwarf star, the Sun sits comfortably in the middle range of stellar masses and temperatures. There are stars hundreds of times larger, and others barely a tenth its size. Some burn millions of times brighter, while others glow so faintly they're nearly invisible. The Sun's mediocrity is actually fortunate for us. Massive stars burn through their fuel quickly and die young, while the smallest stars burn so dimly that planets around them receive barely enough warmth. Our average star provides stable, consistent energy that has allowed life to evolve and flourish over billions of years. In a universe of extremes, sometimes being average is exactly what you need. Stars are born in vast clouds of gas and dust called nebulae. The birthplace of stars is not a sterile void, but rather beautiful, sprawling clouds of gas and dust known as nebulae. These cosmic nurseries can span hundreds of light years and contain enough material to create thousands of stars. When a region within a nebula becomes dense enough, perhaps triggered by a nearby supernova shockwave or the gravitational influence of passing objects, it begins to collapse under its own gravity. As the cloud contracts, it heats up, spinning faster and faster, eventually forming a dense core that will become a new star. The process can take millions of years, but the result is spectacular. a newborn star igniting for the first time, pushing away the surrounding gas with powerful stellar winds and illuminating the nebula from within. Some of the most stunning images captured by telescopes show these stellar nurseries, glowing in brilliant colors as new stars come to life. The nearest star to Earth is over 4 light-years away. After our Sun, the closest star to Earth is Proxima Centauri, a small red dwarf that sits approximately 4.24 light-years away. To put this in perspective, a light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. Even traveling at the speed of our fastest spacecraft, it would take tens of thousands of years to reach this neighboring star. The vast distances between stars mean that even though the night sky appears crowded with starlight, the space between these celestial objects is almost incomprehensibly empty. If you could somehow travel to Proxima Centauri and look back, our Sun would appear as just another faint point of light in an alien sky. This immense isolation reminds us that stars, despite appearing close together from Earth, are separated by gulfs of space that challenge our ability to truly comprehend distance. Most stars in the universe are red dwarfs. If you were to randomly select a star from anywhere in the universe, chances are overwhelming it would be a red dwarf. These small, cool stars make up roughly 70 to 80% of all stars in existence. Red dwarfs are typically less than half the mass of our Sun and burn their hydrogen fuel so slowly and efficiently that they can survive for trillions of years, far longer than the current age of the universe. Despite being so common, red dwarfs are so dim that not a single one is visible to the naked eye from Earth. The nearest red dwarf, Proxima Centauri, can only be seen with a telescope. Their long lifespans and ubiquity make them fascinating targets in the search for extraterrestrial life, as planets orbiting red dwarfs could potentially remain stable for incredibly long periods, giving life ample time to develop and evolve. Stars come in different colors based on their temperature. The color of a star reveals its surface temperature, creating a beautiful rainbow across the night sky if you know where to look. The hottest stars glow blue or blue-white, with surface temperatures exceeding 30,000 degrees Celsius. Slightly cooler stars appear white, while medium-temperature stars like our Sun shine yellow. As stars cool further, they shift to orange and then red, with the coolest stars barely reaching 3,000 degrees Celsius. This relationship between color and temperature comes from basic physics. The same reason a piece of metal glows red when moderately heated, but shifts to white hot at higher temperatures. Ancient astronomers noticed these color variations, but didn't understand their cause. Today, astronomers use precise measurements of stellar colors to determine not just temperature, but also age, composition, and evolutionary stage, turning starlight into a detailed biography of each distant sun. The largest known star could fit over 1 billion of our suns inside it. Among the most massive stars ever discovered, UY Scuti and Stephenson 2-18 are red supergiant stars, so enormous that their size is difficult to comprehend. If you placed one of these giants where our Sun sits, its surface would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, and Mars entirely. With a radius over 1,700 times that of our Sun, these stellar behemoths could contain more than 1 billion sun-sized spheres within their volume. Yet despite their massive size, these stars are relatively cool and diffuse, with outer layers so tenuous they're almost like a very hot vacuum. These giants represent stars in their final evolutionary stages, having exhausted their core hydrogen and swollen to tremendous proportions. They won't remain this large forever. Eventually, they'll shed their outer layers and collapse, potentially ending their lives in spectacular supernova explosions. Some stars are smaller than the planet Jupiter. At the opposite, extreme from supergiant stars, are the tiny stellar remnants known as white dwarfs and certain brown dwarfs. White dwarfs, the dense cores left behind after sun-like stars shed their outer layers, can be roughly the size of Earth, despite containing about half the mass of our Sun. Brown dwarfs, sometimes called failed stars, never quite achieved the mass needed to sustain hydrogen fusion, and can be even smaller, some comparable in size to Jupiter. What makes white dwarfs particularly remarkable is their incredible density. A teaspoon of white dwarf material would weigh several tons on Earth. These compact objects represent the endpoint for most stars in the universe, including our Sun, which will eventually collapse to Earth size when its fuel runs out billions of years from now. The existence of stars smaller than planets reminds us that size and mass don't always correlate in space. Stars can exist in pairs, or even larger groups. While we're accustomed to our solitary sun, most stars in the universe actually have companions. Binary star systems, where two stars orbit their common center of mass, are extremely common, with estimates suggesting that over half of all stars belong to such systems. Some systems contain 3, 4, or even more stars dancing in complex gravitational relationships. In binary systems, the stars can be very close, orbiting each other in days, or widely separated, taking thousands of years to complete a single orbit. These stellar partnerships create fascinating scenarios. If planets exist in such systems, they might experience multiple sunrises and sunsets, or have wildly varying seasons as they navigate the complex gravitational environment. Close binary stars can also transfer material between each other, sometimes leading to dramatic events like nova explosions, when one star dumps matter onto its companion. Neutron stars are the densest objects in the universe, except for black holes. When a massive star explodes as a supernova, its core can collapse into an object so dense that protons and electrons are crushed together to form neutrons. The result is a neutron star, typically just 20 kilometers across, but containing more mass than our entire Sun. A single teaspoon of neutron star material would weigh about 1 billion tons. The gravity on the surface is so intense that it would flatten a human to a layer just atoms thick. Neutron stars often spin incredibly fast, some rotating hundreds of times per second, and they possess the strongest magnetic fields in the known universe. Some neutron stars, called pulsars, emit beams of radiation that sweep across space like a cosmic lighthouse, allowing astronomers to detect them from thousands of light years away. These extreme objects push the boundaries of physics and help scientists understand matter under the most extreme conditions imaginable. The Sun loses about 4 million tons of mass every second. Through the process of converting hydrogen to helium in its core, the Sun transforms mass directly into energy, according to Einstein's famous equation, E=mc². Every second, roughly 620 million tons of hydrogen fuse into 616 million tons of helium, with the missing 4 million tons converted entirely into energy that radiates outward as light and heat. This might sound alarming, as if the Sun is rapidly wasting away, but in reality, it's barely noticeable. The Sun is so massive that it can continue this process for another 5 billion years before running out of hydrogen fuel. Over its entire 10 billion year lifespan, it will convert only about 0.03% of its total mass into energy. This steady consumption of mass keeps our star shining consistently, providing the stable energy source that makes life on Earth possible. Stars twinkle because of Earth's atmosphere, not because they actually flicker. The romantic twinkling of stars in the night sky has nothing to do with the stars themselves. Instead, it's entirely caused by Earth's turbulent atmosphere. As starlight passes through layers of air with varying temperatures and densities, the light bends and shifts slightly, causing the star's position and brightness to appear to change rapidly. This atmospheric turbulence creates the twinkling effect we see. Planets, by contrast, appear as small disks rather than points of light, so the averaging effect of light from across their visible surface makes them appear to shine more steadily. Astronauts in space, beyond Earth's atmosphere, see stars as steady, unwavering points of light. The same atmospheric turbulence that makes stars twinkle also poses challenges for ground-based telescopes, which is why advanced observatories use adaptive optics technology to compensate for these atmospheric distortions and capture sharper images of the cosmos. The light from some stars we see tonight left those stars before humans existed. When you gaze at the night sky, you're not seeing stars as they are now, but as they were when their light began its journey toward Earth. Some of the brightest stars visible to the naked eye are hundreds or even thousands of light years away, meaning their light has been traveling through space for centuries or millennia. The star Betelgeuse, a red supergiant in the constellation Orion, is about 550 light years away, so we see it as it was during the European Middle Ages. Even more distant stars might appear in our sky as they were before recorded human history. This time delay means we're literally looking into the past whenever we observe the stars. It also means that some stars we see twinkling might have already exploded or changed dramatically, but we won't know until their light, carrying news of those events, finally reaches us. Stars are responsible for creating most elements in the universe. Every atom of carbon in your body, every oxygen molecule you breathe, and nearly every element heavier than helium was forged inside a star. In the beginning, the universe contained almost exclusively hydrogen and helium, but stars act as cosmic factories, using nuclear fusion to build progressively heavier elements in their cores. Small stars create elements up to carbon and oxygen. Massive stars can forge elements all the way up to iron through fusion. Elements heavier than iron, including gold, silver, and uranium, are created during supernova explosions when massive stars die. These explosions scatter newly formed elements across space, where they become part of new nebulae, eventually condensing into new stars and planets. This means that you, and everything around you, are literally made of stardust, recycled remnants of ancient stars that lived and died long before our solar system formed. Some stars pulse regularly, expanding and contracting like a beating heart. Variable stars change in brightness over time, and one fascinating category is pulsating variables. These stars physically expand and contract in regular cycles, growing larger and dimmer, then shrinking and brightening repeatedly. The most famous are Cepheid variables, which pulse with periods ranging from days to months. The expansion and contraction happen because the star becomes unstable at certain stages of its evolution, creating a feedback loop where increased pressure causes expansion, which leads to cooling and contraction, which leads to heating and expansion again. The regularity of these pulses is so precise that Cepheid variables serve as standard candles for measuring cosmic distances. Astronomers can determine how far away a Cepheid variable is by measuring its pulsation period, a discovery that revolutionized our understanding of the universe's scale and led to the realization that galaxies exist far beyond our own Milky Way. The Sun will eventually become a red giant and consume the inner planets. Our Sun, currently in the stable middle phase of its life, won't remain unchanged forever. In about 5 billion years, when it exhausts the hydrogen fuel in its core, it will begin fusing hydrogen in a shell around the core, while helium accumulates at the center. This process will cause the Sun to swell dramatically, expanding to perhaps 250 times its current diameter. As it grows, the Sun will likely engulf Mercury and Venus entirely, and possibly Earth as well. Our home planet, if not consumed, will be stripped of its atmosphere and baked to a lifeless cinder. The red giant phase will last for roughly 1 billion years before the Sun finally sheds its outer layers, creating a beautiful planetary nebula and leaving behind a white dwarf core that will slowly cool over trillions of years. This distant future scenario is a reminder that stars, even stable ones like our Sun, undergo dramatic changes over cosmic timescales. Ancient Polynesian navigators used stars to cross vast ocean distances. Long before GPS or even compasses, Polynesian wayfinders navigated thousands of miles across the Pacific Ocean using only the stars, ocean swells, and subtle environmental cues. They memorized the positions of hundreds of stars, knowing where each would rise and set throughout the year. By following star paths, sequences of stars that rise in the same location throughout the night, navigators could maintain their heading even as individual stars moved across the sky. They passed this knowledge down through generations via oral tradition, creating mental star maps of incredible precision. Using these techniques, they successfully colonized remote islands across a vast triangle of ocean, stretching from Hawaii to New Zealand to Easter Island. This remarkable feat of celestial navigation demonstrates humanity's ancient connection to the stars and shows how understanding the night sky enabled exploration and discovery long before modern technology. Stars can orbit around black holes without being consumed. Near the center of our Milky Way galaxy lies a supermassive black hole called Sagittarius A, and astronomers have observed stars orbiting incredibly close to this gravitational monster. These stars move at astonishing speeds, some reaching several % of the speed of light as they whip around the black hole in highly elliptical orbits. Despite coming frighteningly close to the event horizon, they survive their passage because they move fast enough that their orbital velocity prevents them from falling in. Observing these stellar orbits has provided some of the strongest evidence for black holes' existence and allowed scientists to measure the black hole's mass with remarkable precision. The fastest of these stars, designated S2, completes an orbit around Sagittarius A in just 16 years, covering a path that brings it within just 17 light hours of the black hole, closer than our Sun is to Neptune. Brown dwarfs are failed stars that never quite ignited. Brown dwarfs occupy a strange middle ground between planets and stars. They form like stars, condensing from clouds of gas and dust, but they never accumulate enough mass to sustain hydrogen fusion in their cores. With masses typically between 13 and 80 times that of Jupiter, they're too massive to be planets, but too small to be true stars. Some brown dwarfs can fuse deuterium, a heavy form of hydrogen, generating some heat and light. But this process is brief and limited. As a result, brown dwarfs slowly cool and dim over time, making them increasingly difficult to detect. Astronomers have found brown dwarfs with atmospheres containing clouds of iron and silicate minerals, and some are cool enough to have water vapor and even methane in their atmospheres, similar to giant planets. These objects help astronomers understand the transition between planets and stars and the minimum mass required for stellar ignition. The apparent magnitude system for measuring star brightness dates back to ancient Greece. The system we use today to measure how bright stars appear in the sky has roots in the work of the ancient Greek astronomer Hipparchus, who classified stars into 6 categories or magnitudes, with first magnitude being the brightest stars visible, and 6th magnitude, the faintest. This somewhat counterintuitive system, where lower numbers mean brighter objects, has been refined and extended, but remains fundamentally the same. Modern astronomy has made the scale logarithmic and precise, defining it so that a difference of 5 magnitudes represents a brightness ratio of exactly 100 to 1. The scale now extends beyond what ancient astronomers could see, with the Sun at magnitude -27, and the faintest objects detected by space telescopes reaching magnitude 30 or fainter. This ancient classification system's persistence shows how foundational observations made thousands of years ago continue to shape modern science. Massive stars live fast and die young compared to smaller stars. In the stellar world, size and longevity are inversely related in a dramatic way. Massive stars, those with 8 or more times the mass of our Sun, burn through their nuclear fuel at prodigious rates, shining brilliantly but briefly. A star 20 times the mass of the Sun might exhaust its fuel in just 10 million years, a cosmic blink. In contrast, small red dwarf stars burn so slowly and efficiently that they can survive for trillions of years, thousands of times longer than the current age of the universe. This happens because massive stars need much higher core temperatures and pressures to support their enormous weight, which dramatically accelerates fusion reactions. The most massive stars live such brief lives that they can form, evolve, and explode as supernovae within the same era, while the smallest stars born at the universe's beginning are still contentedly fusing hydrogen today and will continue doing so for eons to come. Betelgeuse might explode as a supernova any time in the next 100,000 years. Betelgeuse, the prominent red supergiant star marking the shoulder of Orion, is a star living on borrowed time. It has already exhausted the hydrogen in its core and is now fusing heavier elements in a desperate attempt to stave off gravitational collapse. Astronomers know that Betelgeuse is nearing the end of its life and will eventually explode as a supernova. But predicting exactly when is impossible with current knowledge. It could happen tomorrow, or it could happen 100,000 years from now. Either way, when it does explode, it will be spectacular, becoming bright enough to see easily during the daytime for weeks, possibly outshining the moon. Recent dimming episodes observed in Betelgeuse sparked excitement that the supernova might be imminent, but the star has since recovered. When this supernova finally occurs, it will offer astronomers an unprecedented opportunity to study a stellar death throes from relatively close range, just 550 light-years away. The Sun's core is much hotter than its surface, but the corona is even hotter than both. The Sun's structure defies simple logic. The core, where fusion occurs, reaches temperatures of about 15 million degrees Celsius, hot enough to fuse hydrogen into helium. As you move outward through the Sun's layers, the temperature drops, and the visible surface, or photosphere, is a relatively cool 5,500 degrees Celsius. But then something strange happens. Moving farther outward into the Sun's atmosphere, the temperature suddenly skyrockets. The corona, the Sun's outer atmosphere visible during total solar eclipses as a pearly white halo, reaches temperatures exceeding 1 million degrees Celsius. This coronal heating paradox has puzzled scientists for decades. How can the outer atmosphere be hundreds of times hotter than the surface below it? Current theories suggest that magnetic energy, generated by the Sun's internal dynamo, is released into the corona through reconnection events and waves, but the exact mechanisms remain an active area of research. Stars can steal matter from their companion stars. In close binary star systems, gravity and orbital dynamics can create a cosmic dance of theft and exchange. When one star swells during its evolution, or when two stars orbit particularly close together, material from the larger or less dense star can flow toward its companion through a point called the Lagrangian point, where gravitational forces balance. This transferred material spirals inward, forming an accretion disk around the receiving star before eventually crashing onto its surface. In systems where one star has already evolved into a white dwarf or neutron star, this mass transfer can have explosive consequences. Material accumulating on a white dwarf can trigger runaway fusion reactions in nova eruptions. Matter falling onto a neutron star can release enormous amounts of X-ray energy. In the most extreme cases, a white dwarf can accumulate enough stolen mass to exceed a critical threshold and explode completely as a Type Y supernova, obliterating both stars in the process. The concept of stellar parallax helped prove that Earth orbits the Sun. For centuries, critics of the heliocentric model argued that if Earth truly orbited the Sun, nearby stars should appear to shift position against more distant background stars as our viewing angle changed throughout the year. Since no such stellar parallax was observed, they concluded Earth must be stationary. They were right about the principle, but wrong about the conclusion. Stellar parallax exists, but stars are so incredibly far away that the shift is tiny. It wasn't until 1838, when Friedrich Bessel made extremely precise measurements of the star 61 Cygni, that stellar parallax was finally detected, providing direct proof that Earth indeed orbits the Sun. The measurement also allowed the first direct calculation of a star's distance. Today, stellar parallax remains a fundamental technique for measuring cosmic distances, with space telescopes like Gaia mapping the positions and parallaxes of over 1 billion stars with unprecedented precision. Wolf-Rayet stars are massive stars shedding their outer layers at tremendous rates. Wolf-Rayet stars are among the most extreme objects in the stellar zoo. Massive stars that have stripped away or blown off their outer hydrogen layers, exposing their helium-rich cores directly to space. These stars generate powerful stellar winds that carry away mass at rates millions of times greater than the solar wind, sometimes losing an entire Earth mass worth of material every year. The intense radiation and particle winds from Wolf-Rayet stars create beautiful, expanding nebulae around them, illuminating the surrounding space with their fierce light. These stars are rare, because they represent a brief but spectacular phase in massive star evolution, occurring just before the star explodes as a supernova. Wolf-Rayet stars also burn incredibly hot, with surface temperatures exceeding 40,000 degrees Celsius, making them appear intensely blue-white and contributing to their classification among the hottest stars known. The fusion process in the stars creates energy because mass is converted directly into energy. The heart of what makes stars shine lies in Einstein's most famous equation, E = mc2. When hydrogen nuclei fuse together to create helium, the resulting helium nucleus weighs slightly less than the sum of the individual hydrogen nuclei that formed it. This missing mass hasn't disappeared. It's been converted into energy. Because the speed of light squared is such an enormous number, even tiny amounts of mass convert into tremendous energy. In the sun's core, roughly 620 million tons of hydrogen fuse into 616 million tons of helium every second, with 4 million tons of mass converted purely into energy. This energy initially takes the form of high-energy gamma rays, which then spend thousands of years bouncing around inside the sun, gradually losing energy and shifting to visible light before finally escaping into space. This mass-energy conversion is the fundamental power source for all stars and the reason they can shine for billions of years. Some stars explode as supernovae, briefly outshining entire galaxies. When a massive star exhausts its nuclear fuel, its core collapses catastrophically in less than a second, rebounding in one of the universe's most violent events, a core collapse supernova. For a few weeks, this single exploding star can outshine the combined light of all 100 billion stars in its galaxy. The explosion releases more energy in seconds than the sun will produce in its entire 10 billion year lifetime. The blast wave, traveling at a significant fraction of the speed of light, slams into surrounding gas and creates beautiful expanding supernova remnants that can glow for thousands of years. Supernova are crucial cosmic events. They synthesize and scatter heavy elements throughout space, trigger the formation of new stars by compressing nearby gas clouds, and leave behind exotic remnants like neutron stars or black holes. Ancient astronomers recorded several supernovae as guest stars that appeared suddenly in the sky, sometimes visible even during daytime, before gradually fading over weeks or months. The Hertzsprung-Russell diagram maps stellar evolution and classification. In the early 20th century, astronomers Einar Hertzsprung and Henry Norris Russell independently created a diagram that revolutionized our understanding of stars by plotting their luminosity against their temperature or color. This Hertzsprung-Russell diagram revealed that stars don't scatter randomly across the plot, but instead fall into distinct groups. The majority of stars, including our Sun, lie along a diagonal band called the main sequence, where stars spend most of their lives steadily fusing hydrogen. Giant and supergiant stars occupy the upper right, being cool but incredibly luminous due to their enormous size. White dwarfs cluster in the lower left, hot but dim because of their small size. By placing a star on this diagram, astronomers can infer its age, stage of evolution, and ultimate fate. The HR diagram transformed stellar astronomy from mere observation into a predictive science, allowing astronomers to understand not just what stars are, but how they change over time. Magnetars have the strongest magnetic fields in the universe. Among neutron stars, an extreme subset called magnetars possesses magnetic fields trillions of times stronger than any magnetic field produced on Earth. These fields are so intense that they warp the very structure of space around them and can affect atoms thousands of kilometers away. If a magnetar existed at just half the distance to the Moon, its magnetic field would be strong enough to erase every credit card on Earth and disrupt electronic devices. Magnetars occasionally experience starquakes when their crust fractures under magnetic stress, releasing bursts of gamma rays and X-rays so powerful that they can affect Earth's atmosphere from thousands of light years away. During one particularly intense magnetar flare in 2004, the blast temporarily overloaded detectors on several spacecraft, despite occurring 50,000 light-years away. These objects represent matter and energy pushed to their absolute extremes, creating conditions impossible to reproduce anywhere else in the universe. Ancient Chinese astronomers kept detailed records of supernova observations. Long before modern astronomy, Chinese imperial astronomers maintained careful sky records as part of their duties, believing celestial events held significance for earthly affairs. These records, spanning over 2,000 years, include detailed observations of guest stars, bright stellar appearances that we now recognize as supernovae and novae. The most famous is the 1054 AD supernova that created the Crab Nebula, recorded by Chinese astronomers as a star bright enough to see during the daytime for 23 days and visible at night for nearly 2 years. These ancient records are invaluable to modern astronomers because supernovae in our galaxy are rare, occurring perhaps once or twice per century. By identifying the dates and positions of historical supernova, astronomers can study their present-day remnants and understand how these structures evolve over centuries. The meticulous observations made by ancient astronomers continue to contribute to cutting-edge science more than a millennium later. Star formation is still actively occurring throughout the universe. Stars aren't just ancient relics from the universe's past. They're being born even now in vast molecular clouds scattered throughout galaxies. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery just 1,300 light-years away, where hundreds of stars are currently forming. Infrared observations can peer through the dust to reveal protostars, young stellar objects still gathering mass from their surrounding clouds. These newly forming stars are often surrounded by protoplanetary disks, flattened clouds of gas and dust where planets will eventually form. Some regions of star formation, like the Carina Nebula, are creating massive stars whose intense radiation and stellar winds sculpt the surrounding gas into fantastic shapes. The process continues throughout the universe, with an estimated rate of several new stars forming per year in a typical galaxy like the Milky Way, ensuring that the stellar population constantly renews itself. The Sun rotates, but not as a solid body. Unlike a planet made of rock or gas, the Sun doesn't rotate uniformly. Different parts of the Sun rotate at different speeds in a phenomenon called differential rotation. The equatorial regions complete a rotation in about 25 days, while regions near the poles take 35 days or more. This differential rotation is possible because the Sun is composed entirely of plasma with no solid surface. This uneven rotation plays a crucial role in generating the Sun's magnetic field through a process called the solar dynamo. As magnetic field lines get twisted and tangled by the differential rotation, they can emerge through the surface, creating sunspots, solar flares, and coronal mass ejections. The 11-year solar cycle, which sees the number of sunspots rise and fall regularly, is driven by this complex interaction between rotation and magnetic fields. Understanding solar rotation helps scientists predict space weather events that can affect satellites, power grids, and communication systems here on Earth. Some binary stars orbit so close they share a common atmosphere. In the closest binary star systems, two stars can orbit each other with such a small separation that their outer atmospheres actually touch and merge, creating a contact binary. These systems consist of two stars sharing a common outer envelope of gas while maintaining separate cores. The most extreme examples are called Ursa Majoris variables, where the two stars orbit in just hours, locked in a gravitational embrace so tight that they appear almost peanut-shaped. Material can flow freely between the two stars, and they share heat, making both stars appear similar in temperature, despite potentially having different masses. These contact binaries represent an unstable configuration, as the two stars will likely merge completely over time, possibly creating a single rapidly rotating star, or leading to other dramatic evolutionary outcomes. They provide natural laboratories for studying stellar evolution in extreme environments and testing theories about how stars interact when brought into intimate contact. The photons we see from the Sun's surface were created in its core thousands of years ago. When a photon is created in the Sun's core through fusion reactions, it doesn't immediately stream out into space. Instead, it begins an incredibly long and chaotic journey through the Sun's dense interior. The core is so packed with matter that a photon can travel only a tiny fraction of a millimeter before being absorbed by an atom and re-emitted in a random direction. This process repeats countless times, with the photon taking a random walk through the Sun's layers. Despite moving at the speed of light, the photon's path is so tortuous and convoluted that it can take anywhere from 10,000 to 200,000 years to work its way from the core. Star formation is still actively occurring throughout the universe. Stars aren't just ancient relics from the universe's past. They're being born even now in vast molecular clouds scattered throughout galaxies. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is a stellar nursery just 1,300 light-years away, where hundreds of stars are currently forming. Infrared observations can peer through the dust to reveal protostars, young stellar objects still gathering mass from their surrounding clouds. These newly forming stars are often surrounded by protoplanetary disks, flattened clouds of gas and dust where planets will eventually form. Some regions of star formation, like the Carina Nebula, are creating massive stars whose intense radiation and stellar winds sculpt the surrounding gas into fantastic shapes. The process continues throughout the universe, with an estimated rate of several new stars forming per year in a typical galaxy like the Milky Way, ensuring that the stellar population constantly renews itself. The Sun rotates, but not as a solid body. Unlike a planet made of rock or gas, the Sun doesn't rotate uniformly. Different parts of the Sun rotate at different speeds in a phenomenon called differential rotation. The equatorial regions complete a rotation in about 25 days, while regions near the poles take 35 days or more. This differential rotation is possible because the Sun is composed entirely of plasma with no solid surface. This uneven rotation plays a crucial role in generating the Sun's magnetic field through a process called the solar dynamo. As magnetic field lines get twisted and tangled by the differential rotation, they can emerge through the surface, creating sunspots, solar flares, and coronal mass ejections. The 11-year solar cycle which sees the number of sunspots rise and fall regularly, is driven by this complex interaction between rotation and magnetic fields. Understanding solar rotation helps scientists predict space weather events that can affect satellites, power grids, and communication systems here on Earth. Some binary stars orbit so close they share a common atmosphere. In the closest binary star systems, two stars can orbit each other with such a small separation that their outer atmospheres actually touch and merge, creating a contact binary. These systems consist of two stars sharing a common outer envelope of gas while maintaining separate cores. The most extreme examples are called Ursa Majoris variables, where the two stars orbit in just hours, locked in a gravitational embrace so tight that they appear almost peanut-shaped. Material can flow freely between the two stars, and they share heat, making both stars appear similar in temperature, despite potentially having different masses. These contact binaries represent an unstable configuration, as the two stars will likely merge completely over time, possibly creating a single rapidly rotating star, or leading to other dramatic evolutionary outcomes. They provide natural laboratories for studying stellar evolution in extreme environments and testing theories about how stars interact when brought into intimate contact. The photons we see from the sun's surface were created in its core thousands of years ago. When a photon is created in the sun's core through fusion reactions, it doesn't immediately stream out into space. Instead, it begins an incredibly long and chaotic journey through the sun's dense interior. The core is so packed with matter that a photon can travel only a tiny fraction of a millimeter before being absorbed by an atom and re-emitted in a random direction. This process repeats countless times, with the photon taking a random walk through the sun's layers. Despite moving at the speed of light, the photon's path is so tortuous and convoluted that it can take anywhere from 10,000 to 200,000 years to work its way from the core to the surface. Once it finally reaches the photosphere and escapes into space, it takes just 8 minutes to travel the 150 million kilometers to Earth. This means the sunlight warming your face today began its journey in the sun's core long before human civilization emerged. T Tauri stars are young stars still settling into stable fusion. Before a star reaches the main sequence and begins steadily fusing hydrogen, it goes through a tumultuous adolescence as a T Tauri star. These young stellar objects, typically less than 10 million years old, are still contracting under gravity and haven't yet reached the stable equilibrium of mature stars. T Tauri stars vary unpredictably in brightness, sometimes changing significantly over just days or hours. They often display powerful stellar winds and dramatic jets that shoot material away from their poles at high speeds. Many T Tauri stars are surrounded by protoplanetary disks where planets are beginning to form, making them crucial for understanding planetary system formation. Their strong magnetic fields, active surfaces, and variable nature make them far more dynamic than sedate, main sequence stars like our Sun. Observing T Tauri stars gives astronomers a window into what our own solar system might have looked like 4.6 billion years ago, when the Sun was young and temperamental. The Sun contains 99.86% of all mass in our solar system. Despite the impressive sizes of planets like Jupiter and Saturn, and despite the countless asteroids, comets, and dust grains spread throughout the solar system, the Sun utterly dominates the mass budget. All 8 planets, all their moons, the asteroid belt, the Kuiper belt, and everything else combined make up less than 0.6% of the solar system's total mass. This enormous mass concentration is what keeps all the planets in orbit through gravitational attraction. Jupiter, the largest planet, contains most of the remaining mass at about 0.1% of the total, making it roughly 1,000 times less massive than the Sun. This mass distribution is typical for stellar systems, with the central star containing the vast majority of matter, while planets and other objects share the small remainder. The Sun's gravitational dominance extends far beyond the visible planets, holding sway over distant comets in the Oort cloud, nearly a light year away. Stars can be used as cosmic lighthouses to measure the expansion of the universe. Type Ia supernovae have a special property that makes them incredibly valuable to cosmology. They all reach nearly the same peak brightness, making them standard candles whose distance can be determined by comparing their apparent brightness to their known intrinsic luminosity. In the 1990s, two teams of astronomers used type Ia supernovae to measure distances to galaxies billions of light years away and made a shocking discovery. Not only was the universe expanding, as had been known since the 1920s, but the expansion was actually accelerating. More distant supernovae appeared dimmer than expected, suggesting they were farther away than simple expansion would predict. This observation led to the concept of dark energy, a mysterious force causing the universe's expansion to speed up over time. This discovery earned the 2011 Nobel Prize in Physics and revolutionized our understanding of the universe's composition and fate, revealing that about 70% of the universe consists of this strange dark energy. The Chandrasekhar limit determines whether a star becomes a white dwarf or explodes. In the 1930s, astrophysicist Subramanian Chandrasekhar calculated a critical mass limit for white dwarf stars. He found that electron degeneracy pressure, the quantum mechanical force that holds white dwarfs up against gravity, can only support a maximum mass of about 1.4 times the Sun's mass. Below this Chandrasekhar limit, a white dwarf can exist stably, slowly cooling over billions of years. But if a white dwarf exceeds this limit, perhaps by accreting matter from a companion star, nothing can prevent gravitational collapse. Or the carbon and oxygen in the white dwarf ignite in a runaway thermonuclear explosion that completely destroys the star in a type Ia supernova. This limit is fundamental to stellar evolution, determining the fate of stars and explaining why type Ia supernovae reach similar peak brightnesses. Chandrasekhar's work, done while still in his 20s, was initially controversial, but eventually earned him the Nobel Prize and revolutionized our understanding of stellar endpoints. Blue stragglers are old stars that appear mysteriously young. In ancient star clusters, where all the stars formed at roughly the same time, astronomers noticed something puzzling. While most stars had evolved off the main sequence, becoming red giants or white dwarfs as expected for their age, some stars appeared blue and bright, as if they were young and freshly formed. These blue stragglers seem to defy stellar evolution. The mystery's solution likely involves stellar collisions or mass transfer in binary systems. When two stars merge, or when one star steals mass from a companion, the resulting star or rejuvenated star can appear more massive and younger than it should. With more fuel to burn, it shines brighter and bluer than other cluster members. Blue stragglers are more common in dense globular clusters, where stellar collisions are more likely, and studying them helps astronomers understand the complex interactions that can occur in crowded stellar environments. Sunspots appear dark, but are actually quite bright. When you look at images of the sun, sunspots appear as dark blemishes on its surface. This darkness is relative, an illusion created by contrast. Sunspots are regions where strong magnetic fields suppress convection, reducing heat flow from the interior and making those areas about 1,400 degrees cooler than their surroundings. At roughly 4,000 degrees Celsius, sunspots are still incredibly hot and bright. If you could somehow isolate a sunspot and view it against empty space, it would glow brilliantly, far brighter than the full moon or even an arc welder. They appear dark only because they're surrounded by even hotter, brighter surface material at 5,500 degrees. Sunspots vary in size from small pores, barely larger than Earth, to massive groups that could swallow dozens of Earths. They appear, evolve, and disappear over days to weeks, driven by the dynamic magnetic processes occurring beneath the sun's surface. The sun's future evolution will create a planetary nebula. When the sun exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant before eventually shedding its outer layers in a series of gentle pulsations. These ejected layers, enriched with carbon, nitrogen, and oxygen created during the star's life, will expand outward at tens of kilometers per second. The hot, exposed core left behind, a white dwarf with a surface temperature exceeding 100,000 degrees, will illuminate this expanding shell with intense ultraviolet radiation, causing the gas to glow in beautiful colors. This glowing shell is called a planetary nebula, though it has nothing to do with planets. The name comes from early telescopic observations when these objects appeared disc-shaped like planets. Planetary nebulae come in stunning varieties of shapes, from spherical shells to butterfly wings to intricate hourglass structures, shaped by magnetic fields, stellar rotation, and binary companions. They last just tens of thousands of years before dissipating into space, seeding the galaxy with elements that will become part of future stars and planets. Proper motion reveals that stars move through space. Although we think of stars as fixed points in the fixed stars, they're actually moving through space at substantial velocities. Most stars move slowly enough that their positions appear unchanged over human lifetimes. But precise measurements reveal that all stars have proper motion, gradual drift across the sky, relative to more distant background objects. Barnard's star, the second closest star system to Earth, has the largest known proper motion, moving about 1 moon diameter across the sky every 140 years. Over thousands of years, the familiar shapes of constellations gradually distort as stars move in different directions at different speeds. The Big Dipper, for instance, will look quite different 50,000 years from now. This stellar motion reflects the fact that all stars orbit the galaxy's center, with velocities influenced by their locations and the gravitational pull of the galaxy's mass. Measuring proper motion helps astronomers calculate three-dimensional stellar velocities and understand the dynamics of our galactic neighborhood. Some stars are so old they contain almost no heavy elements. The first stars to form in the universe, just a few 100 million years after the Big Bang, condensed from gas that was almost pure hydrogen and helium. These population 3 stars, as they're called, contained essentially no heavier elements because none had been created yet. All heavier elements, what astronomers call metals, had to be forged in stellar cores and supernovae. Although no population 3 stars have been definitively observed, they should still exist. They would have been massive and short-lived, dying quickly and enriching their surroundings with the first heavy elements. Astronomers have found extremely old stars with remarkably low metal content, likely from the second generation of star formation. These ancient stars provide windows into the early universe's conditions and help trace how stellar generations have gradually increased the universe's chemical complexity. Our Sun is a relative latecomer, enriched with heavy elements from countless previous stellar generations. Stellar winds can carry away significant fractions of a star's mass. Stars don't just sit quietly in space. They constantly shed material through stellar wind, streams of charged particles flowing outward from their surfaces. The Sun's solar wind is relatively gentle, carrying away about 1 million tons per second, an insignificant fraction of its total mass. But massive stars and evolved giants produce far more powerful winds. Red supergiant stars can lose an entire solar mass worth of material over just 100,000 years through their intense stellar winds. Wolf-Rayet stars shed mass even faster, with wind velocities reaching several thousand kilometers per second. These powerful winds enrich the interstellar medium with processed elements and can sweep surrounding space clear of gas and dust. The pressure from stellar winds, combined with radiation pressure from starlight, helps regulate star formation by blowing away the raw materials needed to make new stars, creating a natural feedback loop in the galactic ecosystem. Stars can spin hundreds of times per second as pulsars. When a massive star's core collapses to form a neutron star, conservation of angular momentum causes it to spin incredibly fast, much like an ice skater spins faster when pulling in their arms. The fastest spinning neutron stars, called millisecond pulsars, rotate hundreds of times per second, with the current record holder spinning 716 times per second. This means the surface is moving at a significant fraction of the speed of light, creating extreme conditions. These rapid rotations are stable because neutron stars are so dense and compact that their tremendous gravity holds them together despite the extreme centrifugal forces. Many pulsars emit beams of radio waves from their magnetic poles, and as the star rotates, these beams sweep across space like a lighthouse. When Earth lies in the path of the beam, we detect regular pulses with extraordinary precision. Some pulsars keep time better than atomic clocks, making them valuable tools for testing physics in extreme conditions. The Sun's mass creates a gravitational well that warps spacetime. According to Einstein's general relativity, mass doesn't just pull on objects through force, it actually curves the fabric of spacetime itself. The Sun's enormous mass creates a gravitational well, a distortion in spacetime, that causes nearby objects to follow curved paths we perceive as orbits. This isn't just theoretical. Astronomers have measured. Some stars orbit each other so quickly, they complete an orbit in minutes. Among the most extreme binary systems are ultra-compact binaries, where 2 white dwarfs, or a white dwarf, and neutron star, orbit each other in extremely close proximity. The shortest period system discovered so far, HM Cancri, consists of 2 white dwarfs orbiting each other every 5.4 minutes at a distance closer than Earth's diameter. At such close separations, the stars aren't even round, they're stretched into egg shapes by tidal forces. These systems lose energy through gravitational waves, ripples in space-time predicted by Einstein, causing the orbits to gradually shrink. Eventually, in millions or billions of years, The two stars will merge in a violent collision that might trigger a supernova or create a single, more massive white dwarf. Ultra-compact binaries are important sources of gravitational waves that future space-based detectors hope to observe, providing a way to study gravity in its most extreme regimes. The temperature and pressure in a star's core would vaporize any known material instantly. The conditions inside stellar cores are almost impossible to comprehend. In the Sun's core, temperatures reach 15 million degrees Celsius, and pressures exceed 250 billion times Earth's atmospheric pressure. In more massive stars, cores can exceed 100 million degrees, and pressures thousands of times higher. No material we know can withstand such conditions. Any solid or liquid would instantly vaporize into plasma, a state where electrons are stripped from atoms. At these temperatures and pressures, matter behaves according to principles of plasma physics and quantum mechanics, rather than the familiar chemistry of everyday experience. The intense conditions allow quantum tunneling to occur, where particles can overcome barriers they classically shouldn't be able to penetrate, enabling fusion reactions that wouldn't otherwise happen. Understanding these extreme states of matter requires sophisticated physics and helps explain not just stars, but other high-energy phenomena throughout the universe. Herbig-Haro objects show newborn stars announcing their presence. When young stars are still hidden deep within their natal clouds of gas and dust, they reveal their presence through spectacular Herbig-Haro objects, narrow jets of material streaming away from the star's poles at hundreds of kilometers per second. These jets, guided by magnetic fields, slam into surrounding gas clouds, creating glowing shocks visible even through the dust. The jets can extend for light years, creating knotty structures that change visibly over just years or decades as material races outward. Herbig-Haro objects are signs of violent starbirth, where excess angular momentum and material is ejected along the rotation axis, while the equatorial material falls inward to feed the growing star. The spectacular shapes and colors of these objects, visible in infrared and optical wavelengths, make them some of astronomy's most beautiful phenomena. They also provide crucial information about the star formation process, revealing the complex interplay between gravity, rotation, and magnetic fields that shapes newborn stellar systems. Stars can exist in galaxies moving away from us faster than light. Due to the expansion of the universe, galaxies sufficiently far away are receding from us at velocities exceeding the speed of light. This doesn't violate relativity, because the galaxies aren't moving through space faster than light. Rather, space itself is expanding between us and them. Stars in these distant galaxies experience the same physics as stars nearby. Their light takes billions of years to reach us, showing us galaxies as they were in the distant past. The farthest galaxies we can observe are so distant that the light we receive left them over 13 billion years ago, when the universe was young. These ancient galaxies contain stars very different from those nearby, typically more massive, hotter, and metal-poor. Observing these distant stellar populations helps astronomers understand how star formation has evolved over cosmic history, and how the first galaxies lit up the universe after the Dark Ages following the Big Bang. Carbon stars have more carbon than oxygen in their atmospheres. Most stars, including our Sun, have atmospheres where oxygen is more abundant than carbon. But in certain evolved stars, nuclear fusion has created and dredged up so much carbon that it exceeds oxygen abundance, creating carbon stars. These stars appear distinctly red and have unusual spectra showing strong molecular carbon compounds, rather than the oxygen-bearing molecules typical of most stars. Carbon stars play a crucial role in enriching the galaxy with carbon through their powerful stellar winds. Much of the carbon in the universe, including the carbon in our bodies, was created in and expelled from carbon stars. When asymptotic giant branch stars, a late evolutionary phase, develop carbon-rich atmospheres, they often produce sooty particles of carbon in their atmospheres, similar to smoke from incomplete combustion. These carbon grains can eventually be incorporated into planetary systems, providing some of the raw materials for organic chemistry and potentially life. The Eddington limit determines how bright a star can shine. For any given mass, there's a maximum luminosity a star can achieve, known as the Eddington limit. Above this brightness, the outward pressure from radiation becomes so strong that it overcomes gravity and blows the star apart. This happens because photons can transfer momentum to matter through interactions with electrons. When radiation pressure exceeds gravitational force, material gets pushed outward faster than gravity can pull it back. For the Sun, the Eddington limit is about 30,000 times its current luminosity. Massive stars naturally shine close to their Eddington limit, which is why the most massive stars can't exceed about 150-200 solar masses. Any larger, and they'd be unstable. Some exotic objects like luminous blue variables occasionally exceed the Eddington limit in outbursts, losing mass rapidly. Understanding this limit helps explain why stars have maximum masses and why the most luminous stars are also the most unstable and short-lived. Exotic stars made of quarks might exist but remain unconfirmed. Normal neutron stars are composed of neutrons packed together at nuclear density, but theoretical physics suggests that at even higher densities, neutrons might break down into their constituent quarks, creating quark stars. These hypothetical objects would be even denser than neutron stars and might have unusual properties, such as being perfect conductors of electricity or having surfaces. If they exist, quark stars would be difficult to distinguish from ordinary neutron stars without extremely precise measurements of their masses and radii. Some astronomers have identified candidate objects that might be quark stars based on their properties, but no definitive confirmation has been made. The existence or non-existence of quark stars would provide important constraints on the physics of matter under the most extreme conditions, testing our understanding of quantum chromodynamics and the fundamental forces governing quarks. The universe might be hiding these exotic stars among the population of compact objects we've already discovered. Stars can be gravitationally lensed, creating multiple images. When light from a distant star passes near a massive object like a galaxy or black hole, the space-time curvature can bend the light path, creating multiple images of the same star, or making it appear brighter through a phenomenon called gravitational lensing. Einstein predicted this effect, and it was first observed during a solar eclipse in 1919, helping confirm general relativity. On cosmic scales, entire galaxies can act as gravitational lenses, magnifying and distorting background stars and galaxies. In some cases, a nearly perfect alignment creates Einstein rings, complete circles of light surrounding the lensing mass. Gravitational lensing has become a powerful astronomical tool, allowing observations of objects that would otherwise be too distant and faint to see, helping measure dark matter distributions and enabling studies of the early universe. When a star passes in front of another star from our perspective, even without a massive lens, the foreground star's gravity can briefly brighten the background star through microlensing, a technique now used to detect planets. The Volt-Russell theorem suggests a star's mass determines its fate. In the 1920s, Heinrich Vogt and Henry Norris Russell independently proposed that a star's mass and composition completely determine its structure, evolution, and fate. Given the mass and initial chemical composition, the laws of physics dictate everything else: temperature profiles, luminosity, lifetime, and ultimate endpoint. While later refinements showed this isn't quite absolute, mass rotation and magnetic fields also matter. It remains largely true that mass is destiny for stars. A star with 8 times the Sun's mass will become a supernova and leave a neutron star, while one with half the Sun's mass will become a red dwarf for trillions of years. This deterministic quality allows astronomers to model stellar evolution mathematically and predict a star's entire life cycle from observing its current state. It's a powerful principle, showing that the universe operates by comprehensible physical laws, even when dealing with objects as complex as stars. Solar flares release energy equivalent to billions of nuclear bombs. The Sun's magnetic field sometimes becomes twisted and tangled, storing enormous amounts of energy. When this energy suddenly releases through magnetic reconnection, the result is a solar flare, an explosion of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. The largest flares release energy equivalent to billions of 1 megaton hydrogen bombs exploding simultaneously. Though this energy is spread across the electromagnetic spectrum rather than being a kinetic explosion, these flares can accelerate particles to nearly the speed of light and heat plasma to tens of millions of degrees. When directed toward Earth, solar flares can disrupt radio communications, damage satellites, create beautiful auroras, and in extreme cases, threaten power grids and astronauts. The famous Carrington event of 1859, the largest recorded solar storm, caused telegraph systems worldwide to fail and created auroras visible near the equator. Understanding and predicting solar flares is crucial as our technological civilization becomes increasingly dependent on vulnerable electronics and satellite systems. Some stars appear to slow their rotation as they age. Young stars typically rotate much faster than old stars, a pattern observed across stellar populations. The Sun, for instance, rotates once every 25 days, but young Sun-like stars often spin in just a few days or even hours. This slowdown occurs through magnetic braking, where the star's magnetic field interacts with its stellar wind. The wind carries away angular momentum, gradually spinning the star down over hundreds of millions of years. This process is so regular that astronomers can estimate a star's age by measuring its rotation period and temperature, a technique called gyrochronology. Like tree rings recording a tree's age, rotation rates archive stellar ages. However, magnetic braking eventually becomes inefficient for very old stars, and other factors like gravitational interactions can complicate the picture. Nevertheless, the age-rotation relationship has proven valuable for dating stars and understanding stellar evolution, particularly for stars similar to our Sun. Runaway stars race through space at extraordinary velocities. Most stars orbit the galaxy at relatively sedate velocities determined by their location, but occasionally a star acquires a massive velocity kick, sending it racing through space at hundreds of kilometers per second. These runaway stars can form through several mechanisms. In binary systems, when one star explodes as a supernova, the companion can be flung away at high speed like a stone from a sling. Alternatively, close encounters in dense star clusters can give stars velocity boosts through gravitational interactions. Some runaway stars move so fast, they'll eventually escape the galaxy entirely, becoming intergalactic wanderers. As they plow through the interstellar medium at supersonic speeds, they create bull shocks, visible as glowing arcs of compressed gas. Studying runaway stars helps astronomers understand binary star evolution, supernova mechanisms, and the dynamics of stellar clusters, while providing natural laboratories for studying shock physics in space. The nearest star system, Alpha Centauri, is actually 3 stars. When we look at Alpha Centauri, the closest star system to our Sun, we're actually seeing a triple star system. Alpha Centauri A and B are Sun-like stars orbiting each other every 80 years, while Proxima Centauri, a small red dwarf, orbits the pair at a much greater distance. Proxima is currently the closest individual star to us at 4.4 light-years, just slightly closer than the AB pair. All 3 stars are bound gravitationally and travel through space together as a stellar family. Recent discoveries have revealed that Proxima Centauri hosts at least 2 planets, including one in the habitable zone where liquid water could exist on a planet's surface. This makes Proxima Centauri b the closest known exoplanet to Earth and a prime target for future searches for life beyond our solar system. The Alpha Centauri system provides a nearby laboratory for studying stellar dynamics and planetary formations in multi-star systems. Stars can have planets orbiting in retrograde motion. Most planets orbit their stars in the same direction the star rotates, a consequence of forming from a rotating disk of material. But astronomers have discovered hot Jupiters, massive planets very close to their stars, orbiting backward in retrograde motion, opposite to their star's rotation. This unexpected configuration likely results from gravitational interactions with other planets or passing stars that flip the planet's orbit after formation. Some systems show extreme angles with planets orbiting nearly perpendicular to the stellar equator. These misaligned systems challenge simple models of planetary formation and evolution, showing that planetary systems can undergo dramatic rearrangements during their lifetimes. The existence of retrograde planets demonstrates that planetary systems are dynamic environments where gravitational interactions can produce configurations quite different from our orderly solar system. Studying these unusual architectures helps astronomers understand the full range of outcomes in planet formation. The concept of stellar nucleosynthesis explains where most elements come from. In the 1950s, physicists including Fred Hoyle worked out how stars create elements heavier than hydrogen and helium through stellar nucleosynthesis. They showed that hydrogen fusing to helium, helium fusing to carbon and oxygen, and subsequent fusion reactions in massive stars could produce elements up to iron. Elements heavier than iron required different processes: rapid neutron capture during supernovae and neutron star collisions. This theory, outlined in a landmark 1957 paper, explained the observed abundances of elements throughout the universe and showed that we are literally made of stardust. Every carbon atom in your DNA, every calcium atom in your bones, every iron atom in your blood was forged in the core of a star or created in a supernova explosion. This profound realization connects human existence intimately with cosmic evolution, showing that understanding stars means understanding the origin of the matter that makes up everything we know, including ourselves. White dwarfs will eventually become black dwarfs after trillions of years, after a sun-like star sheds its outer layers and leaves behind a white dwarf. That stellar remnant begins a cooling process that will last longer than the current age of the universe. White dwarfs have no internal energy source. They simply radiate away their stored thermal energy gradually over time. Currently, all white dwarfs in the universe still glow at least faintly, because the universe isn't old enough for any to have cooled completely. Eventually, after tens or hundreds of trillions of years, white dwarfs will cool to the temperature of the cosmic microwave background and stop radiating entirely, becoming black dwarfs, dark, cold spheres of degenerate matter, drifting invisibly through space. No black dwarfs exist yet. The universe is far too young. These theoretical objects represent the final, inert endpoint for most stars, including our Sun, a peaceful conclusion to stellar evolution in the unimaginably distant future when the cosmos is old, dark, and cold. Stars can form from the remains of previous stellar generations. Star formation isn't just about pristine hydrogen and helium collapsing under gravity. The nebulae where stars form today are enriched with heavy elements from previous generations of stars that lived, died, and scattered their processed material throughout space. When astronomers analyze young stars, they find metals like iron, carbon, and oxygen in their atmospheres, elements that could only have been created in earlier stars. This recycling process means that stellar populations have gradually increased their metal content over cosmic time. The very first stars, population 3 stars formed from pure hydrogen and helium, would have been very different from stars today, likely more massive and shorter lived. Our Sun is considered a population 1 star, relatively young and metal-rich, made from material that has been through multiple cycles of stellar birth, life, and death. This cosmic recycling connects all stars across time in a great chain of elemental creation and inheritance. The Sun will lose about half its mass when it becomes a planetary nebula. During its red giant phase, the Sun will undergo dramatic mass loss through powerful stellar winds and pulsations that expel material into space. When it finally sheds its outer layers to create a planetary nebula, roughly half the Sun's current mass will be returned to the interstellar medium, enriched with carbon, nitrogen, and oxygen created during the star's life. The remaining core, a white dwarf containing about 0.5 solar masses, will be all that remains of our once mighty star. This mass loss is a crucial part of galactic chemical evolution. Stars gather hydrogen and helium from space, fuse it into heavier elements, and then return much of that processed material to space, where it can be incorporated into new stars and planets. Through this cycle, the galaxy gradually builds up its inventory of heavy elements, the raw materials needed for rocky planets and life itself. Stellar collisions can occur in dense star clusters. In the vast emptiness of space, stars rarely encounter each other closely. But in the dense cores of globular clusters, where hundreds of thousands of stars pack into a region just a few light years across, stellar collisions become possible. When two stars collide, the outcome depends on their types and the collision speed. Low-speed encounters might result in the stars merging to form a single, more massive star, often creating blue stragglers. Higher-speed collisions can be more violent, potentially disrupting both stars or creating unusual objects. Some astronomers believe that certain exotic stars and unusual stellar systems observed in globular clusters are products of past collisions or near-miss encounters. These collisions, though rare on cosmic scales, become significant over the billions of years that globular clusters have existed. Studying stellar collision byproducts helps astronomers understand stellar evolution in environments very different from the quiet stellar neighborhoods, like our Sun's location in the galaxy. Variable stars helped astronomers discover the universe is expanding. In the 1920s, astronomer Edwin Hubble used Cepheid variable stars to make one of the most important discoveries in cosmology. By identifying Cepheids in what were then called spiral nebulae and measuring their periods to determine their intrinsic brightness, Hubble calculated the distances to these objects. He found they were millions of light years away, far beyond the Milky Way's boundaries, proving they were separate galaxies. Then, by comparing these distances with the galaxy's redshifts, measurements showing how light was stretched to longer wavelengths, Hubble discovered a relationship. The farther away a galaxy was, the faster it appeared to be receding. This discovery revealed that the universe itself is expanding, a finding that revolutionized cosmology and led eventually to the Big Bang theory. Variable stars, with their reliable distance measurements, served as the key that unlocked the universe's largest scale structure and evolution. Some stars have been ejected from the Milky Way entirely. Through powerful gravitational interactions, particularly close encounters with the supermassive black hole at the galaxy's center, or with other massive objects, stars can occasionally be accelerated to such high velocities that they exceed the galaxy's escape velocity. These hypervelocity stars race through space at hundreds or even thousands of kilometers per second, fast enough to escape the Milky Way's gravitational pull entirely. Over millions of years, they'll travel out beyond the galaxy's edge into intergalactic space, becoming lonely wanderers in the vast darkness between galaxies. Astronomers have identified several dozen hypervelocity stars, most appearing to have been flung out from the galactic center. Studying their trajectories backward in time helps map the gravitational potential of the galaxy and understand the dynamics of the central regions. These stellar exiles remind us that even galactic gravitational wells aren't absolute prisons. Extreme events can liberate stars to roam the wider universe. The chemical composition of stars can be determined from their light. When starlight passes through a spectrograph, it separates into a rainbow spectrum crossed by dark absorption lines. Each element and molecule absorbs light at specific wavelengths, creating a unique spectral fingerprint. By analyzing which absorption lines appear in a star's spectrum and how strong they are, astronomers can determine the star's chemical composition, temperature, pressure, and even its motion toward or away from us through Doppler shifts. This technique, spectroscopy, reveals that stars are mostly hydrogen and helium, with small amounts of heavier elements. Subtle differences in composition help astronomers classify stars by age and origin. Metal-poor stars likely formed early in the galaxy's history, while metal-rich stars like our Sun formed more recently from enriched material. Spectroscopy transforms starlight from a pretty twinkle into a detailed chemical analysis, showing that we can understand the composition of objects trillions of kilometers away without ever visiting them. Stars can trigger the formation of new stars through their deaths. When massive stars explode as supernova, they don't just scatter heavy elements, They also send powerful shock waves racing through surrounding molecular clouds. These shock waves can compress gas clouds, increasing their density and triggering gravitational collapse that initiates new star formation. This process creates a cascade where one generation of stars triggers the birth of the next, leading to sequential star formation in regions of space. The spectacular pillars of the Eagle Nebula, made famous by the Hubble Space Telescope, show exactly this process. Dense pillars of gas and dust, compressed by radiation and winds from nearby young, massive stars, are actively forming new stars at their tips, even as they're being eroded away. This self-propagating star formation helps explain why stars often form in clusters and associations rather than in isolation, and why star formation regions can remain active for millions of years. Globular clusters contain some of the oldest stars in the universe. Orbiting the outskirts of the Milky Way like a halo, about 150 globular clusters contain hundreds of thousands to millions of stars packed densely together. Most remarkably, nearly all the stars in a globular cluster formed at roughly the same time, making them excellent laboratories for studying stellar evolution. The stars in globular clusters are among the oldest known, with ages of 12 to 13 billion years, formed when the universe itself was young. Their extreme age is revealed by their chemical composition. They contain very few heavy elements, because they formed before many stellar generations had enriched the galaxy with metals. Studying globular clusters helps astronomers understand the early history of galaxy formation and provides constraints on the age of the universe. The beautiful spherical swarms of ancient stars also create a gravitationally intense environment where stellar encounters and exotic objects like blue stragglers, millisecond pulsars, and X-ray binaries are more common than in the calmer regions of the galactic disk. The Sun's convection zone creates its magnetic field through dynamo action. The outer third of the Sun's interior is a convection zone where hot plasma rises from deeper layers, cools at the surface, and sinks back down in a continuous churning motion, similar to boiling water. This convection, combined with the Sun's rotation, creates a complex dynamo that generates and sustains the Sun's magnetic field. As the Sun rotates at different rates at different latitudes, differential rotation winds up magnetic field lines like twisting a rubber band. These tangled magnetic fields eventually emerge through the surface as sunspots, coronal loops, and other active regions. The entire magnetic field configuration reverses polarity approximately every 11 years, creating the solar cycle that drives variations in solar activity. Understanding the solar dynamo helps predict space weather events and explains similar magnetic activity observed in other stars. The process shows how rotation and convection in stellar interiors create complex, time-varying magnetic fields that significantly affect stellar behavior and appearance. Some stars pulsate so regularly they can be used as cosmic clocks. Certain types of pulsating variable stars, especially millisecond pulsars, maintain such precise and stable periods that they rival or even exceed the accuracy of atomic clocks. Millisecond pulsars, neutron stars spinning hundreds of times per second, can maintain their rotation periods constant to within a few microseconds over years. This extraordinary precision makes them valuable tools for fundamental physics research. Arrays of pulsars scattered throughout the galaxy are being used as a galaxy-sized gravitational wave detector, with astronomers monitoring tiny timing variations that might indicate gravitational waves passing through space. The regularity of pulsars also helps test general relativity in strong gravitational fields and provides natural standards for timekeeping that are independent of human technology. These cosmic clocks demonstrate nature's ability to create phenomena of remarkable regularity and precision, far surpassing what humans could build until quite recently. Stars in the galactic halo orbit in random directions unlike disk stars. The Milky Way's structure includes not just the familiar spiral disk, but also a roughly spherical halo of old stars surrounding it. While stars in the galactic disk, including our Sun, orbit in the same general direction, like cars on a highway, halo stars orbit in all different directions with highly elliptical paths that carry them through the disk and back out again. This chaotic orbital structure reflects the halo's formation early in the galaxy's history through different processes than the disk. Many halo stars likely formed in small satellite galaxies that were subsequently torn apart and absorbed by the Milky Way. The random orbital directions of halo stars mean they move very fast relative to the Sun and other disk stars, sometimes called high-velocity stars, even though they're not actually moving unusually fast in absolute terms. Studying halo stars provides clues about the galaxy's formation history and the process by which galaxies grow through mergers and accretion. The most massive stars end their lives as black holes. When the most massive stars, those exceeding about 20 to 25 solar masses, exhaust their nuclear fuel and explode as supernovae. The core that collapses is so massive that not even neutron degeneracy pressure can halt the collapse. The core continues contracting past the neutron star stage, compressing matter to infinite density and creating a black hole, a region of space-time where gravity is so strong that not even light can escape. This stellar mass black hole, typically between 5 and 50 solar masses, represents the most extreme endpoint of stellar evolution. The black hole is surrounded by an event horizon, a boundary beyond which nothing can return. Material falling toward a stellar mass black hole heats up through friction and compression, often emitting X-rays detectable from Earth. Many stellar mass black holes have been found in binary systems where they're pulling gas from a companion star. These cosmic endpoints of massive star evolution represent gravity's ultimate victory over all other forces. Stellar populations reveal the history of star formation in galaxies. Astronomers classify stars into populations based on their ages and chemical compositions. Population Y stars, like our Sun, are relatively young and metal-rich, found in the galactic disk and spiral arms where active star formation continues. Population 2 stars are old and metal-poor, found in globular clusters and the galactic halo, representing the galaxy's earliest stellar generations. More recent classification schemes recognize additional populations, including an intermediate population that fills the gap. By mapping the spatial distribution and properties of different stellar populations, astronomers can reconstruct a galaxy's star formation history, understanding when and where stars formed over cosmic time. This technique reveals that most stars in the Milky Way formed billions of years ago, with star formation gradually declining over time. Different galaxy types show different star formation histories. Elliptical galaxies formed most of their stars early and then stopped, while spiral galaxies like ours continue forming new stars today, creating a mix of populations that tell the story of galactic evolution. And so our journey among the stars comes gently to a close. We've traveled from the smallest stellar embers to the most massive giants, from the nuclear fires of creation to the spectacular deaths that seed the cosmos with the building blocks of worlds and life. The stars continue their ancient dance, fusing elements, shining across vast distances, and slowly evolving according to the patient rhythms of cosmic time. As you rest here, remember that you are connected to these distant lights in the most fundamental way. The atoms in your body were born in stellar furnaces billions of years ago, making you a living piece of the universe contemplating itself. Let these thoughts drift away, now like stardust on the solar wind. There's nothing more you need to understand, nothing more you need to hold. The stars will continue their slow work whether you're awake or dreaming. If you enjoyed this peaceful exploration, please consider subscribing to the Cozy Curiosity channel, where we bring you fascinating facts to accompany your journey into sleep. Until next time, rest well beneath the vast canopy of stars and let their ancient light guide you gently into dreams.